Okay, hello everybody. I hope you all survived the midterm, take-home midterm and in-class midterm. I'll take a few minutes at the beginning of class here to answer any questions anybody has about the midterm, the in-class midterm, or generally. So any questions? I have the midterm up here, and so we can go through and look at the short answer questions and then also the multiple choice true false questions. So any questions about that or any comments on how it generally was? It'd be good to get some feedback.
Could you go over question 1 on the free response?
Question 1 on the free response. Okay, let's see, get to where that is. You are sailing on a ship without GPS, but with an accurate chronometer, which you set to Greenwich time when you sail from England. What does that mean, setting to Greenwich time? Anybody know?
That means that high noon in Greenwich, it's 12 o'clock in your chronometer.
Right. Okay. And then, by convention, that's sort of the noon at the zero meridian, the zero longitude. And so as you know, here we are in Florida. I think we're 4 hours ahead, 4 hours behind England in terms of our time. So their noon happens 4 hours before our noon, because of course the Earth is rotating and we're catching up to where they were 4 hours ago. Okay, so if you had your clock set to noon in Greenwich, and then you can make an observation, which they used to do in the old days, hardly anybody does anymore. You watch the sun going across the sky, and when the sun is at its highest point, its zenith, you could take a fix on that and say, okay, this is noon, and this is our local noon, and you could compare that to, you look at your chronometer and you say, okay, the noon occurred at some other time in Greenwich. And so the difference in time shows how far the Earth has rotated since it was noon, or how far it has to go until we get to noon, right? So you're sailing on a chronometer, and your chronometer reads 10:20, right? So how much time until noon? What's the difference between 10:20 and noon?
An hour and 40 minutes.
An hour and 40 minutes, okay. And we think about how many degrees of longitude there are on the Earth. Well, there are 360, right? Divided into, by convention, into 180 degrees east and 180 degrees west longitude. Okay, so if you're sailing and it's noon in Greenwich, but it's only 10:20 your time locally, have you been sailing west or east?
West.
West, because just like we lie to the West, Florida here lies to the west of England and Europe. Our time is 4 hours earlier than the time in Greenwich. Okay, so if you take 360 and divide it by 24, you get what?
15.
15, thank you. And so that means that each hour is 15 degrees. So the Earth is rotating 15 degrees of longitude each hour in order to make that 360-degree round trip. And then it's just arithmetic. You're looking at 1.667 hours difference, and multiply that by 15, and you should get the longitude, right? What ocean would you be in? So the longitude, forget what I wrote down for the answer there, but let's see. I got my calculator. Maybe I could.
It's 20 degrees, right?
Well,
Hour. No, wait, no, it's out 25. Hour and 40.
so it's 1 hour and 40, right? So that's 1.667, something like that. 2/3, so it's 1 2/3 hour difference. So if we multiply that times 15,
25.
oops. $25 degrees. So we're at 25 degrees west longitude. Where would that put us?
In the Atlantic, right?
In the Atlantic, right. So that's how you get the answer to question number 1. Any other questions you'd like me to go over? Everything else was straightforward. Good. Hopefully this, the take-home midterm and then the readings and everything allowed you to prepare for this. And so far the grades look pretty good. So I'm assuming everybody did okay. Okay, if you have any other questions about over the midterm or, where you are grading wise, you can contact me or Carrie. And I'll remind everybody, please, when you send emails to me, make sure you copy Carrie, because sometimes she picks up on stuff quicker than I do and vice versa. And, sometimes if you send me something, I need to send it to her. So you can save us a little trouble and make sure that you're most likely to be heard and responded to if you copy both of us. And if you put OCE 4008 or oceanography or something like that in the subject line, then we'll know, that this is a student and we'll respond to you as rapidly as possible. Okay. Any other questions about the midterm or where we're at?
Excuse me, sir.
Go ahead.
I know I wasn't the only student. There's a lot of people who got questions previously correct on different quizzes, but like on the midterm.
Yeah, there was a mismatch, and we're not exactly sure how that happened. Carrie and I have gone over this, and we've resolved that question. So
yeah, everybody, it's all fixed, and everybody's midterms are regraded for those questions.
Thank you.
Okay, sorry about that. That was an error, a bookkeeping error on our part.
Can you go over the question with the depth recorder and the signal?
The depth recorder and the signal. Okay. The depth recorder transmits a signal and receives the echo from the bottom 5.6 seconds later. How deep is the water? Well, this is a pretty easy question if you remember the basic principles. So one of the basic principles is the speed of sound in water. Now that varies according to the temperature, the salinity of the water, and longitude and latitude even. But the rule of thumb that I said was that the speed of sound in water is what? Somebody should know. Do you remember, Charlotte? Speed of sound in water? That's 1,500 meters per second. Okay. So 1,500 meters per second. So that sound has been traveling for 5.6 seconds, right? It goes to the bottom and it comes back 5.6 seconds later. So if we take out our calculator again, I'm not going to bring up the calculator. Well, I might as well. So 1,500 times 5.6. That's the total distance that the sound has traveled, okay? But of course, remember that the sound had to leave the ship, go to the bottom, and then bounce back and come back to the ship again. So what you're looking at there is the two-way travel. And the total two-way distance is 8,400. But in order to figure out how deep the water was, we divide this by 2, and we get 4,200 meters, which is right around the average depth of the ocean. So you're somewhere, far from land, over the main abyssal plain of the ocean, most likely. Okay. Anything else? Free lines of evidence that Tuzo Wilson used. Well, I was looking for the fit of the continents of Africa and South America and Europe and North America, how they fit together like puzzle pieces. That was one line of evidence. Another line of evidence was volcanic island chains like Hawaii. And so the source of the volcanic eruptions is a fixed point, a hot spot, and the fact that there's a chain of volcanoes with the most recent volcano and at the one side of the chain, the beginning of the chain, and the oldest volcano at the far end of the chain, that's evidence that the plate is moving past the hot spot. And then the final line of evidence that he used were transform faults. And those are the faults, those right angle faults, that are perpendicular to the mid-ocean ridges. And the reason that was evidence was because the expansion, the growth of this new seafloor has to accommodate for the curvature of the spherical Earth. And so those cracks, those faults form to accommodate the differential motion across that spherical distance. Okay. 3 types of plate boundaries associated with seafloor splitting. I was looking for convergent, divergent, and transform. So depth recorder, we already talked about. What changes in sediment types? Anybody know the answer to that? So basically, beyond the continental shelf and above the calcium carbonate compensation depth, you get calcareous sediments made of shells and other hard parts of organisms that are composed of calcium carbonate. What happens when you go deeper in the water is that the amount of CO2 dissolved in the water increases, and with that increase in CO2, there's a reduction in pH, increase in the acidity, and so calcium carbonate dissolves, can't form. There are other forms of calcareous material like aragonite that can form in deeper things, but basically fundamental difference is that the calcareous tests of plankton dissolve below the calcium carbonate compensation depth, and what kind of organisms are preserved below there. What kind of planktonic organisms? Those are organisms that have tests or shells made out of siliceous material, which doesn't dissolve. Siliceous is like glass, silicate based. And so you get a transition from the calcareous to siliceous sediments. And what's the approximate depth? 1,500 meters is a pretty good estimate. Okay, how is the ocean stratified and what are the different causes of different strata? I was looking for salinity, temperature. I wanted to see the thermocline, pycnocline. I wanted you to label those basic features. This is an easy one. True or false, the compound sodium chloride does not exist in the ocean. That's true because as soon as you put sodium chloride, salt, into water, it dissolves, and what that dissolution means is that the ions are separated, Cl minus and A plus, and they're surrounded by a little shell of water molecules, and so you don't actually get that compound. It's dissolved. Where do we find the ITCZ and what kind of wind patterns? So this was just looking for the ITCZ, the meteorological equator. And I wanted to see the Hadley cells, the trade winds, and correctly draw a diagram of that. Draw a diagram of an Ekman spiral. I wanted to see that that the arrows were pointing in a spiral, that the length of the arrows got less as you got deeper into the spiral. So that was what I was looking for. And the same thing with the North Atlantic gyre. I wanted to see sort of a circular gyre with the hill of water and the flow of water down, and then the correct direction of the arrows. In other words, that you're getting this clockwise right deflected flow, because the higher water as it flows outward from the top of the mound is deflecting because of Coriolis and because of vorticity to the right. Okay. Any other questions? Okay, good. And so you can anticipate that the final, was there another question?
Yeah, I had a question.
Sure.
I misread, where was that number? I thought it had said, that sodium chloride does exist in the ocean, and then I argued, for false, and then gave the right explanation for it. But would I get points for that if I argued like I explained like the right answer, like how it actually works, but I just misread I missed the word not.
Okay, well, if you gave if you talk about the, dissolution of the compound and, then we'll give you credit. We might knock off something a little bit for not reading totally, but, what I wanted was the concept to understand that, all these ionic compounds are dissolving in the ocean. And once they dissolve, they're present as ions, but not as compounds. So if you got that basic idea right, then you'll certainly get credit.
Cool.
Okay. And I don't think we'll finish the grading. We'll have everything graded pretty quick. I don't know, Carrie, how far along did you get looking at the essay questions?
Not far, because I was fixing the issues we were having.
Okay, so we'll knock that out, and by Monday for sure, or certainly over the weekend, you'll have the final grade on your midterm take home plus in class. Okay. All right, so I started on last Thursday a introduction to the theory of tides, and I want to spend some time on this because tides are important in so many ways. They're one of the principal drivers of energy, and they have huge impacts on the shape of the coast, on so many things. The tidal energy that or the energy that's lost from the rotary system of the Earth and the Moon has actually had the effect of slowing the Earth down. And so the energy that's lost by this in this system of keeping the Moon in rotation is actually slowing down the Earth. And so 500 million years ago, there's evidence to show that the length of the day was about 22 hours as opposed to a little over 24 hours in the present time. And with that shorter day, the number of days in a year was more. So it's more like 400 days in a year. And so, if you think about that in sort of in geologic terms, you get a sense of the scale of the impact that tides have. That's a geologic example. But then there's huge impacts in terms of the shape of coasts and the way that coastlines erode. And we'll look a little bit at that when we think about chapter 12 on coasts. And then there's very, very important for marine organisms, particularly marine organisms living in areas that are affected by tides, but then also tidal forces affect the behavior of organisms and the energy and the resources available to organisms in just a myriad ways. And tides are hugely important for human activities to do with the ocean. So if you look up Florida tides, right away you find that fishermen and fishers generally are very interested in the tide. They want to know if the tide is coming in, going out, when high tide is going to be, those sorts of things. And fortunately, it's we understand tides well enough to where we can predict those. Okay. So we started with this concept of the equilibrium theory of the tides. And the principal tide is this lunar tide called the M2 tide, and the M2 tide is this bulge towards this moon and a bulge on the opposite side of the side of the Earth opposite the moon. And so if the Earth is spinning on its axis, you can see that there'd be two of these, but potentially two tides, high tide and low tide, or two high tides and two low tides in the course of 24 hours. But the dynamic theory of tides, which we introduced at the end of Thursday's lecture, mitigates against that because of the influence of water and so forth. Okay, so the Earth is rotating beneath this tidal bulge, and of course, the other thing is that the lunar orbit is displaced. So the orbit, so, you know, this is a little bit confusing because this is drawn with the axis of the Earth, you know, at 90 degrees to the page. But of course, it's rotated over about 23.5 degrees. And so that's what's reflected in the, but the path of the moon is in the same ecliptic as the orbit of the Earth. So the Earth and the moon and the, you know, the sun are all in a plane, but the axis of the Earth is rotated slightly, well, 23 degrees. And so, you know, that creates this uneven effect on the Earth with respect to north and south. So, you know, this sort of diagrammatically indicates that. And of course, the sun and the moon can operate together. You know, so we have a solar tide and a lunar tide. So there's the S1 tide and the M2 tide. Those are the principal tides. And then these are going to vary in terms of how great they are. Now, important terms are spring and neap tides. And so the spring tide is going to be the highest tide, the greatest tidal range, and that's going to be at times when the Earth and the moon and the sun are all in a line. Okay, and so those are going to be spring tides. And then there's also neap tides, which are lower tidal range when the moon is out of phase. So new moon and full moon are times of high tides, spring tides, and the quarter moons, first and quarter and third quarter moons, are times when the we have lower tidal range because the sun and the moon are working at cross purposes. All right. And so the cycle time, you know, the lunar day is 24 hours and 50 minutes long. Why is it 24 hours and 50 minutes long? Well, the Earth and the moon, the Earth is rotating and the moon is tracking the Earth. So it's rotating in, you know, in the same direction. The Earth is, the moon is orbiting the Earth in the same direction that the Earth is rotating. So because of that rotation of the Earth at the same time that the moon is orbiting it, it takes the moon an extra 50 minutes to catch up to you know, the same relative point on Earth during each day. So the lunar day is 24 hours and 50 minutes long, and so the moon rises 50 minutes later each day because of that gap in time, the catch-up period. And so, you know, the lunar day is 24 hours, and then the M2, you know, there are 2 of these bulges per day, and that has a period, a basic period of 1/2 of this lunar day period time. And the lunar cycle is only 29.51 days because it completes, this is the time it takes to complete the orbit around the Earth. And, you know, if you look at these different things here, they're all sort of different funny fractions. You can think about them in that way. And so this combination of lunar days and you know, 24-hour periods and so forth creates a, you know, a lot of complexity in trying to calculate wherever you are. Fortunately for us, you know, a lot of this has been worked out in terms of tables and expectations. Astronomical cycles are predictable, and so we can work out what the tide should be at any one time. Okay, and then, you know, I'm going to get to the explanation for, so these are the different types of tide that we can have. There's a semi-diurnal tide. Semi-diurnal would be 2 high tides or 2 low tides per day. And there can be a diurnal tide. And in this case, the diurnal tide, example of diurnal tide is for Mobile, Alabama. The same thing would apply for St. Petersburg, Florida. Gulf of Mexico experiences a diurnal tide, 1 high tide and 1 low tide per day. And the reason for that is because of the dynamic behavior of water sloshing around. We're going to get to that, and I'll illustrate that in a way that'll help you understand that. And then there's a mixed tide. where there are still 2 high tides and 2 low tides per day, but there's a higher high tide and a lower high tide, and there's a lower low tide and a deeper low tide. So this is a mixed tide. So these are all different combinations generated by this length of the lunar day. So we can put all this together and look at all these different components here. So these are the components of tides as we describe all this. Spring tides. So this is a sort of a 1/2 month period. So here's the spring tide and here's the neap tide. So this is the time of the lunar month with the greatest range and tide, and then this is the neap tide, is the time of the lunar month with the lowest tidal range. And so you can see that there's a relatively smooth variation in that. And if you remember at the beginning of the lecture, last time I showed you, well, let me show it again just for fun. Here. So, these are all the components. A couple other things that are going on here. The limits of the shoreline, the coast in both maps and charts, so these are, how they're explained here. The highest astronomical tide, the mean high water spring, mean high water neap, mean sea level. That's the, if you subtract all of those tides and take the mean sea level, that sort of is the level of the ocean, the sea level of the ocean, if you remove this variation of the tide. Okay? Mean, and then there's also the mean neap tidal range and the mean spring tidal range and the mean tidal range, and all those sort of come out of all this. And so the depth of the ocean in maps of the land is done with respect to this mean sea level. And the depth of the ocean in the nautical charts is done in relation to the absolute lowest tide. And the reason for that is that they didn't want ships running aground. And they wanted to know what was the minimum depth that ships could experience at any place. And so that was that's the nautical charts then are drawn with respect to that, unless there's some notation to indicate that there's some other data that's being used. Okay? And this is what I showed you before. This is a tide measured in terms of water depth or water pressure due to water depth, and this is measured at a depth of about 547.5 meters depth in the Gulf of Mexico. So here you can see the spring tide and the neap tide, and then this tidal variation is going on. And I showed you this by way of indicating that these tidal forces are uniform everywhere, and everywhere in the ocean there's some signal due to that tide. And so one of the puzzles about deep sea behavior, for example, or deep sea organisms, is how do they know what's going on? How do they know when it's day or night, if they can't see light? Well, one of the effects that reaches organisms is this variation in tide, and also variations in temperature. So more to say about this kind of a chart, but the general idea is that's what's happening. Okay, so that's the then this, all of the diagrams that I've drawn until present sort of imagine a uniform globe surrounded by an ocean of equal depth, and so then the moon is attracting that, and the attraction of the moon is going to produce these bulges. Okay, well, of course, we don't have a uniform ocean depth. We have these things called continents that get in the way of that. And so if we really want to understand what's happening with tides, we have to, and by way of history, Isaac Newton was the first person to come up with a plausible explanation for tides in terms of his theory of universal gravitation. So the theory of universal gravitation says this is always happening. It's constant. These forces are predictable. But the theory of universal gravitation only explains, something like 20% or even less of the observable tidal range, because the world is not constructed like that. So if we want to come up with a more durable theory, we have to do better than Newton. And of course, this began happening, in the 17th century, and people thought about this a lot and realized that we needed to treat the dynamics of water movement. So how these bulges, these waves going around the planet, would respond when they hit the barriers of oceans. So the dynamic theory of tide explains ocean tides based on the sun and the moon acting together, and sort of astronomical effects, celestial mechanics, and the characteristics of fluid motion around barriers that are continents. And then I'm just repeating here, semi-diurnal, lunar, and so forth. So let's dig in a little bit more. I think I covered this a little bit on Thursday, but let's keep going and try to understand this in more detail. We talk about the Earth, the moon orbiting the Earth, and the Earth orbiting the sun, and we sort of think of that, the major body, staying in one place and the orbital body going around it. Well, in fact, two bodies orbiting like that are actually not orbiting one around the other, but they're orbiting around their common center of mass. So in the Earth, that common center of mass is actually interior to the surface of the Earth, and far more interior than is drawn in this picture here. So there's you can sort of understand that in terms of a wrench model, keeping in mind that the center of mass rotation is much, this is greatly exaggerating, that effect. But this model of how the two bodies orbit their center of mass imparts a sort of predictable motion on water. And so, rotation around the path means that, as water responds to this, the forces created by this rotating body and the interaction of the two gravitational fields plus the sun, what this implies is that there's going to be a rotary or orbital energy or forcing for any particle or any water body responding to this change in difference. Okay, so there's an orbital path or for all points on the Earth. So we've got this bulge that's going back and forth, and now the orbital path. Does this remind you of something when we talk? We say that when you look at this and we say, oh, there's this orbital path. Well, what you should be reminded of, or you could be reminded of, is when we drew a picture of a wave. We said that, we have this energy passing through, but that as the wave goes around, the net movement of any floating object or any parcel of water describes an orbit, a circular path. And so that's the way that water responds to a wave energy or wave of energy passing through it. Okay, so this orbital response is happening here. And again, for the purposes of illustration, these circles are hugely exaggerated. Okay, so we got this idea of the equilibrium theory of tides, and now we're saying, okay, that's that explains the range and the fundamental forcing factor that causes this range in water depth over this 24.5 24-hour 50-minute interval. But what does this actually produce? Okay, so now I'm going to show you a video which I found last week when I was putting this thing together. I hadn't seen this before, and I think it's really cool the way that it illustrates what's going on. Okay, so I won't start it quite yet. So what this is made up of I think earlier on, I'm sure I talked about satellites that measure the sea surface height. Well, those are up there, and they're sort of like kind of like tide gauges, orbiting tide gauges, because the way the satellites work, so they're bombarding the Earth all the time with radar energy, and they're taking constant range between the satellite and the surface of the Earth, or most of the Earth is covered with water, so they're taking the range, the distance, and by controlling and correcting precisely for the path of the satellite, they can measure the surface of the Earth, the water, or that distance, with centimeter scale precision, sub-centimeter scale precision, in fact. And so and those kinds of satellites, have really revolutionized and really expanded what we can do as oceanographers and how we can understand the behavior of the ocean surface. Okay, so what this is made up, I think, of 10 years or so of observation from that, and I'm just going to start it running. Hopefully, I'll start running. Here we go.
Ocean tides are not simple. If our planet had no continents, tides would be hemispheric-sized bulges of water moving westward with the moon and the sun. This animation shows the tides as a complex system of rotating and tracked waves with a mixture of frequencies. In many oceans, we see waves rotating clockwise or anti-clockwise, with small amplitudes in the middle of the ocean and high amplitudes around the boundaries, especially along the coasts of Northwest Europe and Britain. Waves are tracked and rotating around New Zealand, causing a high tide on one side of the islands, with a simultaneous low tide on the other side. The TOPIX Poseidon and JASON satellite altimeter missions were designed to observe and record this complexity. Altimeters on these missions acted as flying tide gauges. After several years collecting data, researchers could analyze the signals at each ocean location to determine the tidal characteristics. With that knowledge, plus near perfect knowledge of the motion of the sun and the moon, the tide can be predicted at any location and at any time in the future.
Okay.
Even now, after 3 decades of measurements, we continue to add new details to the picture. The large, short-scale waves on the continental shelves and marginal seas, as well as the polar regions outside the orbits of TOPIX and JASON, are still inadequately known. Scientists expect that SWAT, the Wide Swath Altimeter launching soon, will help improve tidal knowledge in these regions.
Okay, a couple things to notice here. We talked about global amphidromic points, or we're going to talk about that. And these are points of no motion in the ocean. And so you can sort of see that there's a global amphidromic point here. There's another one up here. And so these are places where the ocean, the waves are making this rotary orbital path, but the center, the node of that, there is no tidal range. Okay. Other thing to notice, if you look at this, is the way I'll start it up again. The way that that in some places you see like that there is a sort of a trapping or a lag. So this high water comes in like there, and you can see that the tide goes down, but it takes a while for the water to go down locally. So what's happening there is that the rising tide has caused water to flow into a bay or an embayment or some kind of a enclosed marginal sea. And then when the tide goes down, it takes a while for the water to come out again. So there's the dynamics of the opening to these embayments and gulfs can create lags in the time that the water can move in or out. And I'll show some examples of this. What else do I want to illustrate here? Well, just that, also to point out that, of course, the range here is hugely exaggerated in order for you to be able to see it. Okay. If we start up again, watch the Gulf of Mexico, and you'll see that it's got one cycle per day. All right. So, where other places it's going up and down twice, in the Gulf, it's just a one cycle day. So I think that's a pretty cool diagram, and helps us understand that. And that gives us to understand these global amphidromic points. So this is the model of that I traditionally shown when I give a lecture on this. So these are places where these lines converge, these isobaths of tidal range converge, there's no motion. So a global amphidromic point here, another one here, another one here, one in the middle of the Atlantic Ocean, one in the Indian Ocean, nothing in the South Atlantic. And so, and then if you step away from these, this is the various ranges, all the way up to 11. And if that's feet or what the relative scale of those are. So those are global amphidromic points, and these are points within ocean basins. Okay. Well, this idea of motion in ocean, the same concept of water, of rotary water, can apply when water is flowing into a basin. And we sort of saw some examples of that in that animation of the TOPEX data. So, here's, this is sort of an imaginary, a broad basin. And in a basin, as the water flows in, and then cycles around, this is a place where there would be a diurnal, diurnal tide. There's an area of the basin which is going to have zero tidal range. Okay, and so one of the places where this range is most extreme is in Newfoundland, New Brunswick, Nova Scotia, and so this is one of the parts of the world where you can have a pretty extreme tidal range, as much as in some places you can have as much of a range as 10 or 15 feet of tidal change, so that boats that are floating at high tide are sitting on the bottom at low tide. And so people that own boats in those parts of the world and keep them tied up at docks have to get out and put up sticks and things, the props to keep the boats from tipping over when they ground on the bottom after the tide. So that's a flow in a broad basin, and that's what we were seeing, both with the global amphidromic points and then with the basin amphidromic points that occur within a broad basin. If you have a narrow basin, the water can't quite make that same sort of turn there, and so you can get these very high tides. And so the Bay of Fungi is a place where you get some of the most extreme crests, and here they're telling us that the tidal range in the Bay of Fungi can be as much as 7 meters. So there's a huge tidal range. Now, just as one of the things that come up, and we'll talk about it, I guess, a little bit later, is the idea that we can use this motion of water as we capture some of the energy, huge amounts of energy, huge amounts of water being moved around, and capture some of that energy and use it to generate electricity. And so, one of the places where they've put up one of these tidal generating plants is in Nova Scotia. There's another one in France where they have a similar, very extreme tidal range. Yeah, so this is what we're talking about, the tidal friction, the rise and fall of the tides, and the oscillation of the Earth-Moon system use a lot of energy. And where does that energy come from? Well, it comes from the orbital energy of the Earth-Moon system. And so the length of the day is increasing. So we're being slowed down. The rotation of the Earth is being slowed down by the fact that we're dragging the moon along with us. Okay, just a few vocabulary terms: a flood current and ebb current. So the flood current is when the water is flooding in, and the ebb is when it's flooding out, going out. So flooding and ebbing, the flood and the ebb. And those are sort of poetic terms, the ebbing of this or the flooding of that. And so in poetry, sometimes you'll see this sort of reflection of rising circumstances and falling circumstances. Well, then between the flood and the ebb, you have what's called slack water. And slack water is when there's no net motion of the tide. The outgoing tide is not begun removing water from the shore. So slack water. When you're changing from flooding to ebbing, or from ebbing to flooding. So you can have slack high water or slack low water. Slack high tide, slacking of currents, when the flood has reached its maximum, and then it starts to flow out, and slack water, slack ebb, when the water is at its lowest level and then begins to flood in again. Maelstroms are rotary, sort of whirlpool-like motions of water created by tidal friction on certain kinds of coastlines. And these maelstroms are like whirlpools, and these can be very, very dramatic and dangerous for ships. And so maelstrom, it's a Scandinavian term, I believe, talking about a sort of rotary movement of the water. Okay. Well, here's a bunch of tidal vocabularies: amphidromic point, aphelion, apogee. This is the closest approach of the Earth to the moon, furthest rather. Apogee, aphelion, diurnal tide, dynamic theory, ebb current, equilibrium theory of tides, flood current, high tide, low tide, lunar tide, mean sea level, meteorological tide. What's a meteorological tide? It's variation in the tide caused by onshore winds or offshore winds. Mixed tides, neap tide, node, perigee, slack water, solar tide, spring tide. So these are all sort of vocabulary terms that come out of the discussion that we've been having about tides. All right, well, let's move away from this sort of dynamic and equilibrium theories of tides, sort of the theoretical experience of tides, and then we saw how the theoretical forcing factors that generate these tides are expressed in different ways in different parts of the world, due to the fluid dynamics caused by different coastline and basin shapes. But now let's look at some of the practical effects of tides and some of the ranges that we see. And then we're going to look at, as we move to the end of this lecture, we're going to try to examine some of the changes that are occurring independent of the fundamental astronomical forcing factors. Okay. So, here is an example of low tide on the Pacific shore. And this is a picture from Vancouver Island in British Columbia, where they have this very high tide. And so this is low tide, and you can see that, that the high tide is where these logs and everything have sort of stacked up. So that's the sort of the mean high tide line, and this is something that you'll observe, on the Texas, on the Florida coast rather. You'll observe the mean high tide line in terms of the vegetation. So you'll see where you start to get dune vegetation and grasses growing. Well, that marks, where, beyond the high tide line. So particularly in areas where there's high tide, the change in the tide produces, change in water depth, the salinity, and the nearshore temperature. So, here the sun is heating up all these, these rocks and everything. So there's a huge range in temperature caused by or as a result of alternately being flooded and exposed with the rising or falling tides. And so, the impact of these things, and we'll talk a lot about this when we look at zonation and marine communities. And that's what we're doing, by the way, in the second half of this class. We're going to switch. We've been talking about sort of physical and chemical and geological oceanography. And then I want to switch over and we're going to start talking more about organisms that live in oceans and communities of organisms that form in oceans. And so there's a shift in this part of the course. And looking at tides is a good way to think about that, a good introduction to thinking about those kinds of processes, because the tides produce huge effects on the kinds of organisms that can live there. And so one of the things you see, so this is sort of, again, this is from the same region. So this is a tide pool, and tide pools, if you've had a chance to walk around on rocky shores and places where there are tidal range, tide pools are really exciting, interesting places because you can observe marine organisms. You can look down through this water and you see lots of interesting examples. And right now we're looking at mussels. Mytilus, I'm not sure, Mytilus pacifica, I think probably is this species of mussel here. And so these mussels are all closed up right now. They've got their shells firmly clamped closed because if they had them open, they would dry out. So they have to, the life history and the behavior of these organisms has to accommodate, has to adapt itself to this daily or twice daily exposure that occurs with low tides. And then in these pools, you would find organisms that that sort of take shelter in these little areas. But one of the things to note is that they have this high energy and you have this high range. So you might think this would be a difficult, challenging place for marine organisms to live. Well, it is challenging, and there has to be special adaptations, and there's sort of zonations that are created by this. But fundamentally, the tidal zones are places of very high productivity and high diversity. And so these are favorable places for life to exist because of this energy that that causes the water to flood in and then drain out again. That's constantly supplying nutrients, energy, creating conditions of where productivity can happen. So tidal coasts are some of the most biomass rich, productive species rich regions of the ocean, and that's directly due to this to the energy posed by these tides. So the rise and fall of tidal energy controls the kinds of communities that you can have, and you can this sort of come up with a kind of a theoretical exposure based on where where you are or where the organism is positioned on this. Now you'll notice a lot of the organisms that we've been looking at are what are called sessile organisms. These are organisms that attach themselves and don't move around very much. Sometimes they can move a little bit, but sessile organisms remain attached to some rocky substrate. And this is important in a tidal system because along with these incoming tides and outgoing tides, there's tremendous wave energy. So the organisms need to hang on tight to something to stop from being beaten up by the waves. And but where you choose to attach, yourself as a sessile marine organism is going to determine, what kind of exposures you get, what kind of stresses you get, how often and to what degree you're exposed to air. And so if you're an organism, so that range of conditions determined by, where you put yourself, where you attach yourself, is going to determine what sort of adaptation you need to have in order to survive there. And that range and adaptive pressures creates communities and zonations and organisms. And we'll explore that more, but I just wanted to touch on that because, we're going to be transitioning into this discussion more about marine organisms, marine life, and marine communities. And we can really see a lot of those principles illustrated here in, we look at tidal communities. Okay, well, how do we measure the tide, and what do these measurements tell us long term? Okay, well, we measure the tides, and people have been measuring tides for a long time because they need to know, when it's safe to sail in or out with ships. You've heard the expression, time and tide wait for no man. Well, that was something that used to really determine. People used to travel by ships exclusively, and ships had to sail in and out of harbors. And a lot of harbors had bars, places where there was a low, relatively shallow depths. And so a high tide was needed for boats to sail over those bars. And so, a lot of times you'll see in a movie where the captain is saying, I'm not going to wait. We have to sail on the high tide. I can't wait. And tide wait for no man. So, measurement of tides and prediction of where tides are going to be are very important. Okay, and so this is something from the Delaware River. This is an old timey tide indicator, and here is high tide, slack water, or mean slack water. So that's the zero tidal effect. And this tide gauge is pointing, so this is saying this is going to be in feet. So this is going to say that the tide right now is about 1 foot, maybe 1 foot 4 inches above the mean tidal range, and the downward arrow is saying that the tide is going out. And so if you're sailing your boat and you're concerned about running aground, you better be careful that you don't, get into too shallow water, end up getting stuck. And so that's an example of what they measure with the tide. You can see if you look at this that this is out on a dock. So this is out, position like this, and here you've got some kind of a marker here, which is showing you the range here. This is probably from Newfoundland or somewhere, because the range is very, very high. So there's some floating gauge that goes up and down, and the movement of that gauge is recorded on probably in this old diagram on some kind of a mechanical device. Of course, in modern terms, this is all done digitally. We don't do this anymore, but these tide gauges are, sort of a reminder of how long and how important tides are. Okay, so that's the sort of basic astronomical tides. So we say that the spring, neap, and then the king tides. I forgot to mention king tides. So we said that there's this, spring tides is when the moon lines up, and then neap tides, are when the, so the neap tide is at the, spring tide is when the sun and the moon and the earth are all lined up. The neap tides are when they're at right angles. But then, depending on how close the moon is to the earth and the moon system are to the sun, the gravitational attraction of the sun is going to be greater. So, if you have, a spring tide at a time of the Earth's perihelion, its closest approach to the sun in its annual orbit around the sun, you're going to produce a particularly high tide because the influence of the sun and the moon are going to act together, and the influence of the sun is going to be greater because gravitational energy proceeds as a cube of the distance, and if the distance decreases, then the effect is going to increase. So king tides are times when you get this high range here. Well, these are all astronomical variations in tidal range. And, as noted, tide changes in tidal range due to non-astronomical features occur over geologic times and under conditions of climate change. And so we want to explore that a little bit in the time that we have left. So here are the the effects of non-astronomical tidal change. So what are they? Well, there's crustal motion. We know that the basins are changing, along with plate tectonics, basin formation. So that's a long-term change. We also know that ice sheets and glaciers are melting, and when ice shelves or ice sheets melt, that can put more water into the ocean, and so over glacial cycles or ice age kind of cycles, we can get huge impacts on this. There are also changes due to ocean warming. So the mean temperature of the ocean is going to cause the warmer ocean water expands and has increases the depth, and it's going to increase the tidal range. Wind-driven events. So if there's tend to be stronger winds, that's going to force more water on, and so this barotropic and baroclinic transport are examples of effects that can vary with climates. So these are just a little cartoon of the different factors here. So we can observe this most predictably in if we think about the geologic history of Florida. So about 22,000 years ago was when we had what we call the last glacial maximum, the LGM, and that was when the maximum amount of water was frozen up in the giant ice sheets that covered North America and lots of Europe. Well, with that water, where did that water come from? Well, the water came from the oceans, and so the oceans were at a much lower level, and so 20,000 years ago, what's now coastal real estate would have been very far inland. Well, if all of the ice sheets that remain melt, which is not going to happen tomorrow, but with global warming continuing, we can expect that a lot of the ice sheets are going to melt. I think you get about if all the ice sheets on Greenland were to melt, I think that the total rise in sea level would be on the order of 1 to 2 meters. If all of the ice sheets in Antarctica melt, you can get as much as a 6 or 7 meter increase. And I think this picture here is depicting, what the coast of the south coast of Florida and the Gulf Coast would be like, with a 6 meter rise in sea level. And you can see that it would be very, very bad news if you had beachfront property in Miami. I think we'd basically be okay here in Tallahassee. We would be a lot closer to get to the coast. So maybe the little beachfront property in South Tallahassee might be in order. I don't know exactly where it would fall here. But there are, if you look online and you're interested in that, you can see lots of sort of cartoons that illustrate different levels. Well, what are some other effects that are causing that? Well, the removal of the ice sheets, the glacial ice, has also had an effect on the sort of elevation of the land above the water. So this is something called crustal rebound. So when the glacial ice was sitting on the land, in addition to removing the water from the ocean and causing the amount of water in the ocean to be less, the pressure of that ice on the land actually forced it down a measurable amount. And so, this is sort of crustal subsidence, lowered the level of the land. Well, with the removal of that ice, you get this rebound, and so the land is rising. And so, these are sort of non-astronomical effects which are producing major changes. What are some climate change things that can occur? Warmer air temperatures, warmer surface water temperatures, altered precipitation and hydrologic patterns, altered weather and climate, etc. These are all going to produce different changes. Increases in mean sea level, surface temperature, and so forth. Decreases in ice cover, changes in salinity, alkalinity, wave climate and ocean circulation. These are all sort of on tap as we move into a warmer world. Well, hurricanes and storms, you have to think about that. Right now, the oceanographers and meteorologists are sort of divided. We don't know exactly whether we're going to get more severe storms and waves as a result of climate change. It's beginning to look like we will, that there are real potential differences. We might get, for example, there's a lot of ideas around the fact that, hurricanes have tended to slow down. And so we've had a lot of these effects of hurricanes that basically come in and stall on the coast, and you get this, this long-term flooding. So even a hurricane, which is a relatively modest hurricane, or even just a strong tropical storm like Hurricane Harvey, for example, a couple of years ago, caused tremendous flooding in Texas. And the reason for that flooding was not the intensity of the storm. It wasn't a particularly powerful hurricane in terms of, Saffir-Simpson wind forces, but because it stalled out, it caused like 50 inches of rain to fall in Texas. So that was a major impact. And a lot of that impact was almost certainly due to a warmer world. The other thing that's really interesting about this, sea level concept, we talk about sea level rise as being something that affects coastal areas, but there's also what I like to call sea level rise by air. And so at the same time that there was flooding in Houston and Texas because of Hurricane Harvey, subsequently there was a lot of flooding in the Midwest. And a lot of times we've seen flooding in the Midwest because warmer air temperatures, warmer water temperatures cause greater amounts of evaporation. That evaporated water moves inland and then falls as precipitation, and that can cause an increased flooding. So we're getting a lot of sort of flooding, 100-year floods are occurring on a decadal scale as a result of warmer water. So that's an example of sea level rise by air. So these climate changes are, and we call it sea level rise because where does the water come? It comes from the oceans. Got a lot of stuff on here. Yeah, let me just. Well, okay, so. This is a sort of a diagram of depth in meters, before present. So these are different scenarios for how deep the water was, and what the range was, relative sea level rise. So, relative sea level rise is what we have to consider when we look at, the sort of non-astronomical changes in the extent of tides. We get changes due to increased water temperature, exchange of water with glaciers and ice traps, and human activities. Human activities, can be pretty severe. We can, pumping of groundwater causes saltwater intrusion, and saltwater intrusion can raise tidal effects. Okay, well, I think I will Yeah, let me just show one final graph here. So, this is looking at time before present, and this is sort of showing this ice age effect. And so you can see that there was a very rapid, change in sea level high stand over the last 16,000 years. And that's sort of, evened out. In the present day, the scale is in centimeters, and these are showing recently observed changes in tidal range. And so interestingly, St. Petersburg is experiencing greater tidal range, higher tides, and this scale is in centimeters, not meters. So a 3 centimeter difference, a little bit more than an inch, doesn't sound like much, but that's a tremendous amount of water. And so, one of the, you can remember, I forget which hurricane it was that threatened St. Petersburg, but one of the concerns there was that if it came in at high tide, it would push all that much more water. So a 1 inch increase in tidal range, if you have a hurricane pushing that 1 inch of extra water, across, tens of kilometers of distance, that's a huge change in the volume. So St. Petersburg is one of the places that's really vulnerable to, events that occur because of the relative sea level rise. And of course, Miami is really celebrated for that. And so, here we are at 2020, and we can see that, there's a wide range and a lot of uncertainty about, what sea level rise is going to be like in meters. So it's looking like by the end of this century, by 2100, the sea level rise can be as much as a half a meter higher. Under certain circumstances, it might be much higher. And these are sort of, conservative estimates of what's going to happen. But, we have to remember that there are a lot of nonlinear sort of feedback effects that can occur. And so, people are, one of the things about, sea level rise, climate change, is that scientists are inherently cautious. They don't like to go too far out on a limb. And so when we do our models, whether we're doing models for, predicting this or models for the Intergovernmental Panel on Climate Change, they usually try to be conservative, but every time they recalibrate these models, the circumstances get worse. And so, the rate of melting of the Greenland ice sheets, they've updated that several times, and each time they've updated it, it's like, wait a minute, it's even happening faster than we thought. Same thing with the melting of the ice shelves in Antarctica. So one of the things that's happening in the Antarctica is that you have these ice shelves where there's ice, extending from land, and these huge, floating pieces of ice or, structures of ice. And a lot of these have been breaking off. There was a Manhattan-sized piece that broke off just recently from one of these sheets. Well, when these ice sheets break off, the ice shelf acts as kind of like a cork in the bottle, holding the ice sheet back. And so one thing that, glaciologists and oceanographers are concerned about is that if we break off a lot of these, it's not like there's going to be a steady change, but some of these things could introduce feedback effects that could really accelerate the rate of sea level rise. Okay, well, I'm out of time, so I'll stop there if there are any questions. And we would talk a little bit about coasts next week. But I'm going to focus on primary production, and we'll switch over to looking more at sort of biological oceanography in the lectures to come. So, any questions? Stop sharing. And this is your chance to query or ask anything. I hope you all are happy. It's hard to know. I can't tell whether this is working for you all, but I hope it is. It's material that I really like to present, and I hope you get a chance to absorb this. Okay. Grades will be posted, and we'll be carrying on with our lectures.
Thank you.
Okay, bye-bye. Just looking at the chats, one of the complaints was that there were lots of questions. Well, you'll notice that, I didn't do honor lock, and I don't like honor lock, and I never, I think it just creates a lot of false expectations. But by having a lot of questions, what that does is it says, okay, you have to really know your stuff. It doesn't really let people have enough time to go and look and elicit sort of sources. I would prefer that you just know this material and you can write it out. So that's the strategy that I have and that I've taken for trying to teach in this COVID era. Okay, bye everybody.